Okay, so today topic is electric charge and its field. Already in our earlier lectures, we study about the force produced by a single charge. So by Coulomb law, we find that what is the force of attraction or what is the force of repulsion between any two static charges. So here in electrostatic, we are dealing with a charge having only one type of energy. It is the electrostatic potential energy. The kinetic energy of the charged particle is totally zero. First thing. Second thing is that only and only we can deal with the charged particles. Uncharged particles, they are not taken in this chapter. So charged particle, we know that they are of two types. Either it is a positive charge particle or it is a negative charge particle. Both the charged particles, they impart a force on each other. One charged particle will impart a force on the other and vice versa. Similarly, now today topic is about the field produced by the electric charge. So what is the field? So here we are taking the electric field. Electric field. So what is a field? Before going to the electric field, let us have an overview of the field. So for example, we take the earth and we know that everything fall towards the center of the earth. So it means definitely there is a gravitational field or there is a field around the earth. So within that field, if any object is there, definitely the object will fall towards the center of earth. So this is the gravitational field of the earth. If we take the two magnets and we keep the two magnets in the periphery of each magnet, periphery means it is again a field. So you see that when magnets they are kept close to each other, then they try to attract or they try to repel each other. So it means when they are showing any attraction or any repulsion, so it means they are in the field of each other. So that is the magnetic field. So you can see this is the magnetic field. So again, in the magnetic field, you can see two types of phenomena. Either it is attractive or it is repulsive. But in the earlier case, in the gravitational field, it is only one type of phenomena. It is only the attraction. There is no repulsive force in the gravitational field. Only attractive forces are there. But in the magnetic field, both the forces they are present. So what is a field? What is a field? Field is the space property that is present in the space that is surrounding the object which is emitting that field. Now we go to the electric field because we are dealing with the stationary charges. So if we have the like charges, we know that they will repel each other. The charges will go far away from each other. If we are taking the unlike charges, we will show that they will show the attraction, they will move towards each other. So here repulsion or attraction, it is the outcome of a field. It means there is a field which is surrounding the two charges, whether it is a positive charge or a negative charge, and due to that field we are observing any repulsion or any attraction. So this is because an electric field is formed around an electric charge. And you can see how the electric field is formed. The electric field can be shown around a positive charge, going outside from the positive charge in the form of these lines as shown in the diagram. So space around the charge body, which the influence of charge can be felt. Now, the second term, we have electric field intensity. So electric field intensity, it is electric intensity, it is the measure of strength of an electric field. Like we can find out magnetic field intensity, we can find out gravitational field intensity. So when we are dealing with any field intensity, so that term, whether it is gravitational, magnetic or electric, that term basically that is used to measure the strength of the field. If we are measuring gravitational field intensity, so basically we are interested in finding the strength of the gravitational field. If we are observing magnetic field intensity, so basically we are interested to find the strength of the magnetic field. Similarly, electric field intensity, that will tell us how strong or how weak our electric field is. So basically this term is used to define, to describe the strength of the electric field, how powerful the charge, positive or negative, is creating a field around it, creating a field around it in that space, how strong or how weak. So strongness or weakness is defined in terms of field intensity. When we are dealing with electric charges, so the term is used electric field intensity. Every charge form an electric field around it, positive or negative, both the charges, they will create electric field around them. So the electric field of a positive charge, that can be shown outward lines, and electric field of a negative charge, that can be shown by inward lines. The diagram is not shown here, but you can assume, you can make a picture in your mind. If we have a negative charge, the electric lines or the electric field, that will move towards that negative charge. You just opposite the direction of these arrows and replace the positive with the negative, then you will get the pattern of the field of a negative charge. Now we are interested in finding the strength of field. So for that we have to find out electric field intensity, which is represented by E. So E, electric field intensity, it is force experienced by a test charge placed at a certain distance apart from this positive charge. We have this positive charge and we take a virtual imaginary test charge. Actually there is no test charge, but we are just assuming, because there is no such physical quantity like test charge. It is our imagination that we are putting some test charge, which is represented as q naught, at certain distance, means within the field of the positive charge. If we place this test charge outside the electric field of this positive charge, then our experiment is giving us no result. We cannot find any electric field strength on this test charge. So test charge is placed within the field of the positive charge, and we know that this is the positive charge. Test charge is again assumed to be a positive charge. So definitely this test charge will experience a force of repulsion. So how we will define the strength of this positive charge, how much force of repulsion this test charge experience. So force is experienced F on the test charge, that gives the electric field intensity or the strength of the field over the test charge Q naught. Because force is a vector quantity, charge is a scalar, vector divided by a scalar, we are getting a vector. So electric field intensity is a vector quantity. SI unit, you can find out international system of unit. Force is in Newton, charge is in Coulomb. So Newton per Coulomb. There is one more unit of electric field. There is one more formula. I just tried to write that formula. So electric field E, electric field E, this is electric field E, it is equal to voltage upon distance. Voltage upon distance. So this is the term used from the parallel plate capacitor. If we have two parallel plates and they are connected with a battery, I am connecting them with a battery, positive terminal of the battery, negative terminal of the battery. So the two plates of the capacitor, they are connected with the battery. The voltage of the battery is V. The two plates, they are separated by a distance. This is the distance between the two plates. They are separated by a distance of d. This is the distance between the two plates. So what is the electric field between these two plates? So electric field between these two plates, that can be given by this formula: E is equal to V upon D. So V is in volt, and distance is in meter. So there is a new term, it is electric field. It is also in the unit of volt per meter. So there are two units of electric field. One is from the definition of the field, electric field intensity, which is force upon test charge. So force is in Newton and the charge is in Coulomb. And the second definition, we take two plates, two metallic plates. They are connected with a battery. The voltage of the battery is capital V. The distance between the two plates is small d. So there is an electric field. Electric field means electric lines from one plate, they will move to the second plate. So I just try to show the direction of lines, electric field. They will start from the positive plate and they will go to the negative side. They will start from the positive plate and they will go to the negative sides. So these lines, basically, these lines, they are called the electric lines, represented by this E. This is a vector quantity represented by this vector. We will discuss E is equal to V upon D in detail in our coming lecture. But to describe the unit of E, I am just showing this E is equal to V upon D. V is in volt and this distance is in meter. So there are two units of electric field intensity. One is Newton per Coulomb, other is volt per meter. Now we can find out the dimensions of electric field. So because electric field is made up of two terms, one is the force, other is the charge. So force is in Newton, charge is in Coulomb. So we know the dimension formula of force, which is m raised to the power 1, l raised to the power 1, t raised to the power minus 2. And we also know that Coulomb, it is a derived unit. It can be derived from current and time. So current is in ampere. So it is written as I raised to the power 1 and time raised to the power 1. So finally, we get m raised to the power 1, l raised to the power 1, t raised to the power minus 3, because this t raised to the power 1 in the denominator, when it will go to the numerator, it will become minus 3, and I raised to the power minus 1. So this is the dimensional formula of electric field. Now expression for electric field intensity. So let me rub this. Now we are interested in expression for electric field intensity due to a point charge. So let me take a single point charge Q placed at A. We take another charge, which is a test charge. Test charge is Q naught and Q naught is placed at B. Q naught is again a positive charge. So Q is a charge placed at A, Q naught is a charge placed at B, and the distance between A and B is R. It is a small distance. Q and Q naught both are point charges. And I take a unit vector which is from A to B, and that unit vector is n, small n subscript r, and cap over this. So this cap, basically it is a unit vector. We will discuss some part of the vector also. So in that position vector, unit vector, or different type of vector we will study. So for the time being, you just keep in mind that this is a unit vector, and unit vector, it is directing from A to B. A to B. Because why it is directing from A to B in this case? Because Q is a real charge placed at A. Q naught is a virtual charge placed at B. So the electric field is going outside from A in space in all the directions. We are interested in a particular direction, and that direction is nr unit vector. That direction is nr unit vector. Electric field of this charge q is in space in 3D in all the three directions, but we are interested in one direction because our charge is placed at B. So we are interested only in this particular direction. So that's why this unit vector that will give the direction from A to B. We already know how to calculate the Coulomb force between the two charges. So Coulomb force between the two charges that can be written as F is equal to 1 upon 4 pi epsilon naught Q naught R square and N unit vector. So because force is a vector, so to make this whole expression as a vector expression, we are using this unit vector N cap. Now, how to find out electric field intensity at B? Very easy, because from the definition, E is equal to F upon Q naught. So put the value of F and we will get 1 upon 4 pi epsilon. Q naught is cancelled. So our final equation which is left, E is equal to 1 upon 4 pi epsilon naught Q upon R square and unit vector. So this is electric field intensity uh, in terms of vector. Now, how to find out magnitude of this electric field intensity? So it is also very simple. Electric field intensity in terms of magnitude, simply remove this unit vector from the right side and we will get the magnitude. Now, I repeat it again. We are interested in electric field intensity of this real charge Q naught. So how to find out that? We will take a virtual charge. We will take imaginary charge from our side, which is Q naught placed at B at a distance R from A, and the unit vector from A to B, it is n unit vector. I already told you why we are taking this unit vector, because the field emitted by this charge at A, it is in three directions. We are interested in particular direction. We are interested at point B. So that's why we have to take the help of a unit vector, which will give in the information in which direction we are interested. So first we will find out the Coulomb force between these two charges. F is equal to 1 upon 4 pi epsilon naught Q naught upon R square and unit vector. Because force is a vector, so we will take a unit vector in this expression. Now electric field is equal to force upon test charge. Q naught is cancelled by this Q naught. So final equation is this. And in terms of magnitude of electric field, we just remove this unit vector from the right side, and finally we will get the electric field intensity in magnitude form. Now some questions for you. Very simple question. The unit of electric field intensity is Newton per coulomb, volt per meter, both A and B, none of these. Yes, anyone?
Sir, both A and B.
Okay, good. Both A and B. Already told you Newton per coulomb when E is equal to F upon test charge. So force is in Newton, test charge is in Coulomb. And then second definition, E is equal to V upon D. Potential divided by distance. So potential is in volt, distance is in meter. So we have the both A and B. Which type of quantity is electric field intensity? It is a scalar quantity, it
Vector.
is a vector quantity, it is a tensor, or none of these. Electric
Vector.
field intensity,
Sir,
yes,
vector.
anyone?
Vector.
Vector.
It is a vector quantity. It is a vector quantity. So scalar, it cannot be a scalar, it is a vector. Now there is another term, tensor. So what is a tensor? So already you are familiar with scalar quantities. These are those quantities which can be represented only in terms of their magnitude. Only in terms of magnitude means we do not require the direction, but in vector both
आपकी
magnitude
आवाज नहीं
and
आ रही.
directions they are required. So what is tensor? So tensor is that physical quantity in which three terms are used. The first is scalar, the second is means first is magnitude, the second is direction, and third is the plane. The third is the plane. So, what is the meaning of plane? Plane means, for example, we take pressure. We take a disc which is placed in a river in the vertical direction. So you see that the pressure of the river that will be on the plate, on whole of the plate, and you see the plate has two coordinate. What is first is the x coordinate and second is the y coordinate. So here the pressure is in the two uh, direction, the 2D pressure. So when we are dealing with such type of situation where we need magnitude means how much pressure, the second we need the direction of the pressure, and third we need the distribution of the pressure. So pressure is distributed both along the x-axis as well as y-axis, means pressure is along a plane. So in tensor we have three terms. First is the magnitude, second is the direction, and third is the plane. कि pressure किस प्लेन में है, एक्स वाई प्लेन में है, वाई जेड प्लेन में है, एक्स जेड प्लेन में है, किस प्लेन में है. So three terms are used. Try this one. Electric field intensity is also represented as E is equal to F upon E, E is equal to Q upon F, E is equal to E upon F, or E is equal to F upon Q. Which is the right option? D. E is equal to F upon Q. Actually, I showed you F upon Q naught. So you can take this Q naught also. Okay.
Yes.
Now we have electric field due to a system of charges. So till this point we studied electric field due to a single charge. Now in our day-to-day situation or in our laboratory we will encounter with the situation in which we have a large distribution of charges, and we are interested in electric field due to all these charges. So consider a system of charges having charges q1, q2, qn with the position vector r1, r2, rn relative to some origin. So this will be clear with the help of the diagram. So let me go to the diagram first. So here I am taking a charge q1, and I am interested in finding the field of this charge q1 at point P. So definitely at point P, the field will along this arrow and this will be E1. The distance of this point P from Q1 is taken as R1P because this is Q1 and we want to find out electric field at P. So the distance is R1P. Now we take another charge, Q2, and again we are interested in finding the electric field at point P due to this Q2. So definitely that will be along the line joining this P and Q2, like the line joining of P with the Q1. So electric field is always along the line joining of the point of observation to the actual charge. So this is our point of observation and this is our actual charge. So how to draw the electric field line of Q2 along the line joining? Similarly, how to draw the electric field of Q1 along the line joining of this point of observation to the actual charge. We take another charge Q3, which is at a distance R, 3p from this point, and how to draw the electric field along the line joining of this point of observation from the actual charge q3. So it is along this line. We take another charge q4 at a distance r4p, and how to draw the electric field of q4 along the line joining we can find. So finally, our target is to find out what will be the net electric field at this point P due to all these four charges. So by the principle of superposition, very easily we can find out. So directly we know that how to find out E1. First we will find out E1, then we will find out E2, E3 and E4, and then we will add all of them by the principle of superposition. So we know what how to find out E1. E1 is equal to 1 upon 4 pi epsilon naught Q1 upon R1p square into R1p unit vector. This unit vector, this will give the direction of the field. This will give the direction of the field emitted by this q1, or you can say what information we are getting from this unit vector. This unit vector will tell us way in which direction our point of observation is from the real charge. So r1p, that will give the direction of observation at point P, means at point P what will be the direction of the field. So this R1P, this will give the direction of the field at point P. Now we can find out E2, which is again 1 upon 4 pi epsilon naught Q2 R2P square and R2P. And again R2P, that will give the direction of electric field at point P. Similarly, we can find out E3 and E4. So finally, we will add them all the field E1 plus E2 plus E3, and we will find the final or the net electric field at point P due to all these charges. And this will be our final expression. Put the value of E1, E2, E3 and En, and then we will get this equation. And this equation can be written in this form: E is equal to Q1, because Q1 that can be taken outside, because Q1 that will be present in all the cases. So that can be taken outside. So we can generalize the equation in this form. So finally, E is a vector quantity that varies from one point to another point in space and is determined from the position of the source charges. So this was the method of superposition to find out the net electric field at some point due to a large number of charge distributions. So we will continue with the rest of the lecture in our coming lecture. Okay. Thank you.
Thank you, sir.
Thank you, sir.